Hi everyone. Um, in this video, I'm gonna to solve with you a exercise about thyristors, and is from the book Industrial Electronic from Cyril Lander. And let me draw the the circuitry the circuit and write the exercise. So it consists of a thyristor, mm, and in this exercise we're going to uh, be looking back with some basic concepts so we can understand better. You're gonna see um, why we need to look back a little bit. Um, being more specifically, I'm talking about the RL circuit that I'm going to draw right here. And this thyristor is in parallel with a RL circuit. And this in parallel with other resistor. And maybe you are not familiar with triggered circuits. Um, so in this example, I'm gonna be entering entering with some different specifications like the width, the window of the window width of a pulse, the latching current as well. So right here we have a battery, sorry, a DC source, okay. So this arrangement of these DC sources give us a 100 volts. This resistor, it has 20 ohms. This inductor 0.5 henries. And we want to know this resistor, but let me first read the exercise. So it's about the thyristor with a level of lighting current, and is triggered by a pulse with width of 50 microseconds, and we need to show that this resistor R of the thyristor, the thyristor will not continuing conducting current when the pulse ends, and we need to find the maximum value of this resistor to guarantee that this correct trig, this correct trig. Okay, the exercise give us a solution and say R, without R the current I, and it's already give us this formula, but in this video we're going to work this because it's not nice just throwing up formulas and just follow without knowing where they come from. So that is the formula that is given to us, and this is, I'm gonna explain each term of this formula right now. So I is a current, is the current of the thyristor in a time I, and this big one is the current when we divide the value of the source with the value of 100 volts by this 20 ohms resistor. And exactly, I'm going to working this formula in this video, and you're gonna see where this come from. But the exercise continue, and as I was saying, reading the solution of the book, the resistance R, without these resistors, without this resistance, the current I will be increased exponentially, and that's it. And the solution for this I given by the book is the following. We have this 100 volts over this value of 20 ohms, which gives us a current of 5 amps. The constant T is the value of the inductor divided by this value of resistor. So is 0.5 over 20, which gives us a time constant of 0.025 seconds. And substituting the values after 50 microseconds, we're going to have just substituting in this formula 1 minus Euler exponential minus here 50 microseconds divided by the time constant, and if we do a conversion in this time base, we're going to have a current of 10 milliamps. And the exercise keep going. But before we start thinking what value of R we need to plug right here to guarantee the correct trigger of the circuit, I want to work this equation with you because I think it's gonna be nice. Okay, so right here, let me change the color. We're going to use the Laplace transformation, so we can, because as you already see, this is a time base, so in order to know the value of the current in each time, we need to change this for a time base, and to do this transformation we need to use Laplace domain. So right here we have this. Okay, and for the inductor, V is equal L times the I dt. Okay, that is VL VR. Okay, so in the equation, this is a first order equation, differential equation, and it's IR plus L time, just repeating the equation and passing this for Laplace domain. Let me do this quickly. Okay, let me drag that source, copy that source, and draw a switch, because we need to have a start point, like t equals 0 when the switch closes. Okay, this is a oral circuit you might have already see in your electronic or basic circuit classes. And as the switch closes, so this voltage is applied to the circuit, any voltage. So we're going to have this now with a time base. So is v of t, which is equal of t and now applying the Laplace transformation on each term of this equation. So right here we're going to have it's not complicated. Why? The Laplace transformation is the way that I'm going to write, but this part I'm gonna not be uh, going deeply on this. Okay, and just doing the distributive of L. Okay, and t equals 0 when the switch closes, that is 0, so it's going to remain these terms. And now letting this big I in evidence. And now isolating this big I. And remember, this is Laplace domain, and that is why we are using this S. This is S domain. Is a base of time as well. It's a time base based on Laplace domain. And now reworking this equation, just doing a algebraic manipulation, dividing V by L, and the denominator also divided by L. So if we do this, distributing S on this term, we're going to have this, and dividing by L, so that is V over L divided by S in evidence, or L times S. And when we look for a term which is look like this one, when we substituting the variables on the table of Laplace transformations, we're going to see a similarity on the terms. So now the current I can be determined by taking the inverse Laplace transform of this term that we modulated. So taking the inverse Laplace at each point in time, the current is going to be the inverse Laplace of V over L one over okay. Now what we do is break this in partial fractions. So we will obtain something like A over S plus B over S plus or write this way. Okay, so this is partial fractions, and hope you remember how to solve this, because I just going to write the equations at this first moment. As always, when doing math, we use a variety of resources, and right here is not going to be different. So let's do some algebraic manipulation. Let's multiply both sides of the equation for this term. So we're going to eliminate this term on the left side of the equation. And then after we can expand this, of course, if were the right thing to do. Let's see. I'm missing this S. Same right here. So these terms are going to be, we'll cancel each other here, here, and we are left with the respective equation 1 equal a s plus r over l plus bs. Okay, and from here we can write, as we have now these terms, we can write linear systems and find these terms and determine the way that we're going to obtain the inverse Laplace of this term. First of all, let's apply the distributive on this term, and we are left with this. And now writing the linear equations, this terms matches and they are equal, so we are left sorry, forget about this, the linear. Let's try another strategy for solving this. Exactly. Let's get back um, a step aside and think algebraically to solve this. So if we say s is equal 0, we're going to obtain 0, and this way we cancel b, and e is going to be L over R. And again, thinking algebraically to solve this, if we take s equals to minus R over L, and these values are algebraically uh, choosing exactly to eliminate these variables, and because of this I get a step back and back to this equation, and substituting 0 right here is easy to find a and b. So if we take s being equal now minus R over L, right here we're going to obtain minus R over L plus R over L plus, now is minus B times R over L, and this cancels 0, so we are left with and we can say B is equal minus L over R in this way, and that is the way that we can find B and A to solve this partial fraction. Okay, and now we can rewrite this equation for the given inverse Laplace. Apply it. Okay, let's copy this and drag this. A is equal L over R, and B is equal minus L over R, and rewriting the equation we are left with I of t is equal to inverse Laplace transformation, this big I, Laplace domain as domain, VL to inverse Laplace and now is this partial. Let's use as a reference. It's L over R of S domain, Laplace domain, plus L minus L over R and S plus R over L. And this is the equation that describes the current given a latching current of the thyristor. And this thyristor has a latching current of 50 milliamps. So let's keep with the exercise. We are almost finishing. Okay, now we need to look at the Laplace table of transformations. This term, let's rewrite this L minus L over R times 1 over S plus in this, let's call alpha. Now we can look for this on the Laplace transformation table. And if you look, go ahead and find this term, and you see that lead us to a signal of minus Euler, and the exponential is at u of minus t or t. We have these two transformations for greater than minus alpha and less than minus alpha. Okay, again let's rewrite the equation, and now simplifying even more and making look more pretty, more clear, sweeping a bunch of things. Okay, and now this correspond to this. And we are left with the following. Okay, again repeating the process. RL, it's alpha, so it's 1 over s plus alpha. And if you look this on the Laplace transformation table, you're gonna find this transformation. Over L of t times t, and we can put this term in evidence. So V over L, and letting L over R in evidence, we are left with 1 minus Euler and his exponential. And now we know that this R over L is a time constant, and now V over L, letting this constant outside, and that is the equation that we find on the page 41 of the book that I comment on the intro of the video. Industrial electronic from serial lender. So we find this equation, and this RL is substituted by T, time constant, and I is equal I times 1 over T. Okay? So that is the end. And he says, observe that in this case, how 50 microns is less than the value of the time constant t, which is 0.025 seconds, or I don't know, this might be, let's see, 1, 2, 3, 25 milliseconds, and the initial value of the IDT is equal 100 over 0.5 could be presumed that this constant after 50 microns, giving the current that we find, which is 10 milliamps. If you substitute the values right here, you're gonna find 10 milliamps. After 50 microseconds, the thyristor could not reach the level of latching, being 50 minus 10 milliamps, which is 40 milliamps, which less than the level of 50 milliamps necessarily to trigger the circuit. So the addition of R allows that establishment of immediately of a current of 100 over this R. So the value of R that we can plug in the circuit to guarantee the correct trigger of the circuit is 100, which is the value of the source, the arrangement of the sources, and 50 milliamps, which is the level of latching of the current of the thyristor, minus the 10 milliamps that we find. And this is going to give us a resistor of 2.5 kilo ohms. That is the resistance. Okay, and was the example 1.1, page 41. Okay, that's it. I'm going to leave this video on the playlist of power electronics, and hopefully in the future I can do more exercise about triggered circuits. If you don't know, or if you never work with a trigger circuit, is interesting, just know the waveforms. A typical waveform of a triggered circuit, so this generally used for AC circuits. And let's say you have a AC source, and that is the signal, and that is Vs, and Ig, which is the triggered current, trigger current. His waveform is like this way. So a waveform of a trigger current, a current for trigger, the current that comes from the thyristor, it has this form. It's like a peak, and this is the base of time. We have a time base, and from here you could trigger this current any time of this time base. You could trigger right here, as I'm drawing. You could trigger right here, and that is called the angle of trigger, and this is alpha, which is the angle of the trigger. Okay, for now is just this. Bye bye. Thank you for watching.